Give me a moment. Get some water. It seems weird. After the midterm, like everyone disappeared. Is it like you don't have to take the final or something? Or let me see. Like in spring quarter, there was like an option where like you don't need to take the final if like you count your midterm like a higher percentage. Okay, so today I'm just gonna go over problems on like yeah, but that was like for 140. I don't know if it's true for 120. So I'm just gonna state like some facts, and then we'll do like problems today. So problems on like isomorphism and like I guess cosets, not cosets, normal groups. Sure. Oh, which one? Although I did talk about the homework the last discussion. Were you there, or is there a specific?
Can you use my mic? Is that okay?
Yeah, that's fine.
Yeah. So I guess it was 10.4.
10.4.
So I guess just number one. I'm having a hard time. I guess just like.
So there's two parts. It's the first part is determining if it's normal. Finding the cosets.
Yeah. So from what I understand, it's normal if the left and right cosets are equal. I guess like, is there an easier way to do this without finding the left and right cosets? Because I know there's also like if like. I'm not 100%. It's like something like if like G times N times G inverse is a subset of N, and also if G N G inverse is
Yeah,
equal, then G
that
is equal to N.
Yeah, I suggest you use that because oh, am I sharing? Because in this case, you know that I'm gonna use, instead of G, I'm gonna use sigma. Sigma, like A4 sigma inverse. You prove the theorem that says sigma tau sigma inverse if tau is A1 to AN. It's sigma of A1, sigma of AN, right? Do you remember that, or?
Yeah. Yeah.
Yeah. So you see that conjugating preserves cyclotype, right?
Mm-hmm.
So if so, you see that in this case, since the cyclotype doesn't change, it's still going to be an even number of transpositions. So it's clear that this is is contained in A4, right? And then you're done. So it's normal. So it's easy in the case we're in SN because you have this property right here. Makes stuff very easy because you know what happens when you conjugate.
Okay, so then in this case, I guess to do the problem, you'd basically be checking if this property holds true for the various
So yeah, exactly. But like so you see that for like part B, like it's
Mm-hmm.
not normal because you when you conjugate by something with that sends like 1 to 4, it doesn't remain in H, right? Because H has like no 4 in it.
Yeah.
so,
Mm-hmm.
so you're done. And then I guess C would be like the hardest part. I mean, it's still just conjugating cycles. D and E, it's really like your so part D, it's only 8 elements, right? You could just
Mm-hmm.
check all of
Yeah.
it. And then part
Okay.
E, there's a theorem, right? If you remember, you do see my screen, right?
Yeah. Yeah.
Okay. So in the case, example 10.1, if G is abelian, it's always normal, right? Because
Mm-hmm.
GHG inverse, you can move the G inverse past the H. So you see, in this case, G equals integers, that's abelian. So any subgroup's normal.
Yeah.
Yeah. Are you good? Or do you have any other questions?
I guess just the Calais table then. So then,
Cayley
from what
table.
I understand, yeah, the Calais table uses the left, or like it's like a Calais table of the cosets. My,
Yeah.
uh-huh.
So remember, the cosets. If I have cosets given by G1n, G2n, blah, 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 right? And then there's also n, right? How do you
Yeah.
multiply 2 elements? It's given by G1, G2n. Yeah.
Oh, okay. And then okay, so then you just use that to find the coset. Or
Yeah, it's kind of like how you normally do group operation, right? You just multiply.
okay.
Yeah.
Mm-hmm. Okay, thank you.
Yeah, so do you know there, like this thing, let's say this thing could be equal to like G3n, but it's using like a different representative. Do you get what I mean?
Mm-hmm.
Like you have to make, figure out, like it could, like, for example, um in part, like let's do H. Let's do part A. Like
Mm-hmm.
A4 is H. Anything in A4 times H is equal to EH. So like H is equal to like, get what's something in A4? 1, 2, 3. Yeah. This is certainly true. So what I'm saying is, when you multiply, you could get this coset, but it's given by a different representative. Yeah. So do you get what I mean?
Yeah, sort of. So it's like basically G1, G2 is equal to G3 in the sense that G3 is also in G.
And so yeah, uh well, like, so what I'm saying is, like, in this case, like, uh it could be like G1, G2 gives you this,
Mm-hmm. Yeah.
and then
Okay.
it's actually just EH.
Yeah. Okay.
Yeah. Yeah. So like I'm saying, your Achilles heel might be like all, like, it might look like, different elements, but some of them are like the same. Okay. Any other
Thank
questions?
you. Yeah.
Okay. So I'm gonna talk really quick about simplicity of alternating group. So simplicity. And then we'll do prompts today. So I don't want to go over new content of alternating group. So a group G is simple if and only if it has no non-trivial normal subgroups. So by non-trivial, right? Like, obviously the whole group itself is normal, right? You like G capital G inverse is equal to G because it's a group. So and obviously by non-trivial we exclude like the trivial subgroup, right? The subgroup just given by identity, right? Because identity is always normal, right? The set given by E. But other than that, if we have nothing else, right, it's called simple. So example, you have famous examples called Z mod PZ, right? In fact, this thing is even better. This thing, forget normal, right? It doesn't really have any non-trivial subgroups, right? It's either like the identity, which is 0, or it's the whole group. You have no other subgroups, right? Because every element co-prime the P, which is 1 to P minus 1, generate the whole group, right? So, and then there's a theorem in your book that says that AN for n greater than equal to 5 is simple. Yeah. So, and then the proof, it uses facts about cycles. Let me just say that. You could read it in your book. So you might ask, what about A4? So there exists the Klein 4. Some people call it, I don't know. Some people write it as K4, the Klein 4 group. This group is normal in A4. So you could check. I think it's given by E. Sorry, I don't know why I put braces. So E, and then like the 1, 2, 3, 4, 1, 3, 2, 4, and 1, 4, 2, 3. Yeah. So this thing's normal. And hopefully it's clear, right? Because if you conjugate by anything, right, you're still going to get product of two cycles, and you can only fit 4 numbers in there, right? So you don't have much choice, right? You'll, like, if you conjugate this, you'll end up with either this or this, right? Because I mean, you can only either have 1 and then 3 other numbers, right? You have 1 or 2, 1 or 3, or 1 or 4, and then everything else is determined. So that's an example. Okay, so let's do a problem from the book. So problem 10, H subgroup. So I believe that was you, Andy, who asked. So this is another way you could prove part A of that homework, although it uses more heavy material. H subgroup of index 2 of a group G. So this is more general, right? So in the problem you asked me, A4 was a subgroup of S4 of index 2, right? It's index 2 because order of A4 is half the order of S4, right? So when you divide the order of S4 by order of A4, you get 2. So whenever your subgroup is half the size of your group, H must be normal. Yeah. So I guess part D is also normal if you prove problem 10. Although I guess since you haven't proved problem 10, it's easier to just conjugate by all 8 elements of the quaternion group. Okay. So why is this the case? Well, again, we need to check, since, we don't know much about conjugating, let's use left coset is equal to right coset, right? If this was like Sn, I would probably use the conjugating definition because we know what happens when you conjugate. But since this is an arbitrary group, let's check the left and right cosets are equal, right? So given an element G and G, right? You have 2 cases, right? Either G is in H or G is in G without H, right? I mean, this is certainly, we're not using any fact about index 2 yet. I mean, so in the first case, right, G is in H, then we are done, right? Because since G is in H, GH is equal to HG, right? I mean, H is closed under, multiple, the group operation. So we are done, right? So case 2, G is not an H. Then, so I mean, or if you G not an H, then I can say this, right? That this cannot be true. I mean, hopefully you all know this, right? So what does this mean? Well, this means that GH is equal to G minus H, right? So this is where I'm using its index 2, right? Because my group G, remember cosets partition G, right? And I only have 2, right? I always have H and I have another one. And this is my other one, right? So it partitions G and I only have 2 because from the assumption, right? And since it partitions G, it must be equal to the rest, right? It must be equal to G minus H. And then same for the left, right? So this is left. So right cosets partition G. And I have 2 of them given by HG and, H and HG. So it must be HG is also G minus H, right? And then you're done, right? So they're equal, right? So no index, if it's index 3 or higher, it might not be, right? Because you can have H, and then within G minus H, you can have like, maybe G1H, G2H, right? And then on right cosets, right? On the right coset part, you can have H, G1, H, G2, right? But then HG1 could be G2H, right? And then HG2 could be G1H, right? So it's a problem if the index is 3 or higher, right? If it's 2, you have no choice because you can't be, HG1 cannot be H, so those 2 must be equal. So yeah, so it's really nice fact about subgroups that are half the size. So whenever you have a subgroup that's half the size of your group, it's normal. Yeah. So for example, like Z mod 10Z, the subgroup generated by 2, which is order 5, that's normal. I mean, in that case, the group's abelian, so everything is normal. But yeah. Everyone clear? Okay. So we are gonna do problems on isomorphisms because I feel it's good to do examples about isomorphisms. So let's go here. Let's start with 1. Yeah, prove Z is isomorphic to NZ. Yeah, so note that if it feels weird, right? That like because NZ is a subgroup of Z, right? Yet they're isomorphic. Right, so it's possible for a group to be isomorphic to its subgroup. So n not equal to 0. Okay, so you only have one option, right? Phi, you send Z to NZ. So where do you send the element Z? Well, if you had to, your first guess would probably be this, right? And that's exactly it. That's why it's the first problem in the book, because it's super easy. So it's surjective, right? Because every element in NZ is a form n times Z for up a Z1 for some Z1 in Z. Then the element Z1 maps to it, right? So surjectivity is easy. Injective, right? You assume NZ1 equals NZ2, and then this implies that So let me not skip steps. So remember, injectivity means assume phi of z1 equals phi of z2, and we need to prove z1 equals z2, right? But in this case, phi of z1 is nz1, and phi of z2 is nz2. So it's clear by division that z1 is z2. So we have surjectivity and injectivity. And now we need to check the final property, right? It obeys group law. So let x, y be in the integers. I need to show phi of the operation is plus. So phi of x plus y is phi of x plus phi of y, right? Because in both, both groups are under plus. So let's check it. So phi of x plus y is n times x plus y, and then distributive law, right? Let's distribute the n, and then this is phi of x plus phi of y, right? So this is an isomorphism. Is everyone clear? Okay. So let's do part 2. Proof C star is isomorphic to subgroup of GL and GL2R consisting of matrices of the form AB negative BA. So you need to prove, I'm just gonna call that H, yeah. So again, this is C star. So this is complex numbers without zero under multiplication is isomorphic. I'll call it H, yeah. H is equal to the set of A in GL2R such that A is of the form AB negative BA. Okay, so what should my map be? Right, I'm mapping C star to H. So nobody's gonna tell you the map, so you have to think about it. I mean, how am I gonna get an A and B from complex numbers? Right. What should my map be? By the way, no need to type. I actually prefer if you use your mic so I don't have to keep changing screens. So, I mean, every complex number is of this form, right? I mean, for A, B, and real numbers. So, I mean, if you had to guess, you send it to this, right? So, and so question, why is, why is this well defined? Well, determinant of AB negative BA, hopefully you remember it's A squared plus B squared. But this is the norm of A plus BI, right? So you see, because we excluded 0, determinant is never 0, right? And that means we are invertible. So we are in GL2R. And so this thing makes sense. I mean, it's well defined, right? We're not sending it to a non-invertible matrix. The matrix is invertible because we excluded 0. Everyone clear? Okay. So surjectivity this should be clear, right? I mean, given matrix A, B, negative, B, A, A plus BI maps to it, right? Because everything in H is of this form, right? So, and then injectivity. Well, assume phi of A plus BI is phi of C plus DI. We want to show A plus BI equals C plus DI. Sorry, let me answer that really quick. Okay, back. Okay, so we need to show this, right? So what does it mean for these two to be equal? Well, write it out, right? It means A, B negative BA is CD negative DC. Yeah? So two matrices are equal if and only if every component is equal, right? So this, I mean, from this, you get A equals C, and from this, you get B equals D. So once you have this, it's clear that A plus BI is C plus DI. So injectivity is clear. So the hard part is, I want you all to understand is, you know, the property, right? So the group property, right? So I need phi. In this case, my operation on the left is multiply, right? So I need to show phi of A plus BI, C plus DI is equal to phi of A plus BI. And in this case, on the right-hand side, my operations still multiply, right? The matrices form a group under multiplication. So I need to show this. So let's work with, I'll call this 1 and 2. Let's work with 1. Yeah. If you FOIL, this is what? This is AC minus BD plus AD plus BCI. Yeah. I hope I didn't make algebra error. And then, so where do we, so we know where this gets sent to, right? Like the real part gets sent here, and then the imaginary part gets sent here, right? So my matrix is given by real part gets sent to the top left and bottom right. And then my imaginary part, which is this, AD plus BC, and then the negative of that, right? So this is what the, you know, the left-hand side is. Let's calculate right-hand side. Well, phi of A plus BI is what? It's A, B, negative B, and C, C, D, negative D, right? And then hopefully you all remember how to multiply matrices. You know, you do this with this column, and then with this column, and then this with column and column, right? So A times, so you get AC minus BD, and then the next term is AD plus BC, and then next term is negative BC minus AD, and then the last term is negative BD. And it should be, I mean, these two are equal, right? So we are done. Everyone clear? Hopefully not too confusing. So it's just understanding the group property. I mean, the definition of an isomorphism. Okay, let's do something harder. Let's do, yeah, prove that Q is not isomorphic to Z. Is not isomorphic to Z. So So this will really test whether you understand isomorphism, right? So it really boils down to the group property, right? So let me just guide you. So let's suppose it is, so assume phi from Q. So they're both under plus, right? Q and Z do not form a group under multiplication, right? Q minus 0 forms a group under multiplication, right? So let phi be from Q plus to Z plus is isomorphism. Okay, so I want to first ask you, where does 1 go? Right, 1 has to go somewhere, right? So let's say phi of 1 is, call it some integer m, right, for some m and z. So z without 0. So why can it not be 0? Let me ask that as a first question. So why can 1 not map to 0? So what is 0 in this case? So 0 is the identity, correct? And we must map identity to identity, right? Because again, if you all forgot, G to G prime, right? If I'm saying phi of EG must be EG prime. This has to hold because phi of G is phi of G times E. I mean the E in this group, right? And then by the property, you get phi of EG, right? So if phi of G is phi of G times phi of EG, well, phi of EG better be EG prime, yeah? So you see that phi, in this case, if it's an isomorphism, 0 goes to 0, right? So 1 cannot go to 0, right? Because if 0 went to 0 and 1 went to 0, injectivity fails, right? For injectivity, you can't have two elements mapping to the same element, right? Injectivity will fail. So 1 must map to something that's not 0. So we're just going to call it M. Okay, now question, where does phi of K go for K and integer, K and Z in general? K and Z without 0. We all know where 0 goes. So we're going to consider, because the rationals certainly contain the integers, right? So I'm asking where does the integer 5 go, for example? Yeah, let's start with that. In fact, let's start with 2. What's phi of 2?
Would it just be 2?
No. So let's try to understand. Right? If phi of 1 is m, phi of 2 is phi of 1 plus 1, right? I mean, 2 is 1 plus 1. Now, by the isomorphism property, this has to be phi of 1 plus phi of 1, right? I mean, what I write here is group operation, right? Whatever the operation is. And in this case, the operation on the right is plus. So it's phi of 1 plus phi of 1. And this is m plus m, which is 2m, right? So once you declare where 1 goes, every other integer is determined, right? Phi of 3 by the isomorphism property is this, which is And by the property, it has to be equal to this, right? In which case, it has to be m plus m plus m, which is 3m. Right, so is everyone clear? And let me just convince you for the negative side, right? So question, where does -1 go? This is also determined. Because phi of 0, which we know is 0, right? But on the other hand, this is phi of 1 plus -1. And this has to be phi of 1 plus phi of -1. And we know phi of 1 is m, right? We assume that. So I have m plus phi of -1 is 0. So you see phi of -1 has to be -m, right? So you see every negative integer, like phi of -4, is phi of -1 plus -1 plus -1 plus -1, which by the property of isomorphism has to be this, right? Which is, well, phi of -1 is -m, so -4m, right? Does everyone follow? So once I declare where 1 goes by this property, remember if it's isomorphism, phi of G1, G2 has to equal phi of G1. I'm using this property, right? And then inductively, you get it for, G1, G2, G3, G4. So that's all I'm using. I'm using this and where 1 goes, right? 1 has to go somewhere. So we just call it M. Is everyone clear so far? Great. So in other words, phi of k maps to km, right? If you like phi of -4 maps to -4m. So phi of k maps to km. Agree? So now here's the problem. Where does phi of 1 over m plus 1 go? I mean, this element is certainly a rational number, right? Because m is an integer, right? For some m in the integers. So 1 over m plus 1 is certainly a rational number. Now, where must this map to? I'm claiming this is also predetermined. And this is just a nice property of being rational, right? So to figure out where this goes, right? Let me just write equals what. It's already predetermined by where 1 goes because phi of 1. So on one hand it's m, but it's also 1 over m plus 1 plus 1 over m plus 1 plus 1 over m plus 1. How many times, right? M plus 1 times, right? Everyone clear?
Yes, we clear.
Good. So, and then by the property of isomorphism, it has to be this, right? M plus 1 times. So this is equal to m plus 1, if you like. So dividing by m plus 1, so this has to be m. So phi of 1 over m plus 1 has to be m over m plus 1. And this is a contradiction, right? Because this thing is not an integer. So basically, I'm saying whatever you choose to map 1 to, this element will not map to an integer, right? And that's a problem because phi must map rational numbers to integers. And it can't do that. basically. So hopefully this makes you understand. The only thing I want you all to understand is this part. This is the important part. Like the surjectivity, injectivity. I trust you can all check. But it's this extra property that's new to everyone, right? So you see that this really puts a restriction on your map, right? Because if you have any of you taken math 140, or maybe you heard that both rational numbers and integers are countable. So there are bijective maps from integers to rational numbers and vice versa. But they basically it could be bijective, but it won't satisfy this, right? So you see, like, isomorphism is a much more, it has an extra assumption, right here, that basically puts a restriction on the number of bijective maps. So there certainly are bijective maps. They just don't satisfy this. So yeah. Okay. Any questions so far? Okay, let's do something a bit harder. I'll do part of 9. Yeah. So 9, I have G is the real numbers without -1, and we're gonna define the operation, to be very weird. So A star B is A plus B plus AB. That's our group operation. So I'll let you show, G is a group. Yeah. So that's the first thing. Let's just think it through. 0 is still the identity, right? Because A star 0 is A plus 0 plus A times 0, which is A. So identity is still E. So E is still 0. So that's nice. And then, like, for example, I'll basically, associativity is just a pain. So I'm not going to do that. So, and then to figure out the inverse, well, I need this to be 0, right? Once I know the identity, I can figure out what the inverse is, right? Because on one hand, this is A plus A inverse plus A times A inverse, right? By this property. And this must be 0. So if you just solve, right, I guess, A inverse 1 plus A is negative. So I subtracted -A. So A inverse must be -A over 1 plus A. And this is the part where the fact G equals R minus the negative, R without -1. How do I write it? Yeah, R without. Right? It's important because if I had -1, I would be, -1 has like no inverse, right? Because I can't divide by 0. Okay. So now they want us to show G under this operation. Let's call it star, is isomorphic to R without 0 under multiply. Okay, so really, they don't tell you the map, right? But hopefully you all know the map. So again, I need a map phi. Instead of writing G, I'll write this. Under star goes to R without 0 under multiply. So what should my map be? So a priori, you might think this is weird, right? Like, what should my map? But look at the 2 points that we're excluding, right? So whatever map you make, it better be that, like, -1 gets sent to like 0, right? the two points you exclude should be mapped to each other, right? So because to avoid problematic issues. So question, how do you go from -1 to 0? This should be easy. So what can you do to the number -1 to make it 0?
+1.
Yeah, that should be your first guess, right? Like I need to somehow get rid of the two problematic points, right? So let's map A to A plus 1. So that way there's no problem, right? Like basically I don't want like 5 mapping to 0 because that's a problem, right? So I want -1 to map to 0. So hopefully this search activity is clear. Yeah. I mean, given A in R minus 0, A minus 1 maps to it, right? Because A minus 1 plus 1 is A. I'll let you do injectivity. So really, I want you to understand this part, right? So I want to show phi of A star B. Let me just write leave injectivity to you. It should be a one line like surjectivity. So phi of A star B, we need to show this is phi of A times phi of B, right? Because my operation here is multiply, so it's times. So let's figure out what phi of A star B is, right? This is, again, A star B, by definition, is that weird operation, right? It's A plus B plus AB. So it's A plus B plus AB. And what does phi do to it? Well, it sends it to +1, right? So A plus B plus AB plus 1. And then let's check, what this is, right? This is phi of A is A plus 1, and then times phi of B, which is B plus 1. And if you FOIL, you should get the same result, right? So it's an isomorphism. Everyone, I hope by the end of today, like you all understand like how to prove something's isomorphic, especially like this property, right? So
Wait, how did you get the 1 in the A star B?
well, question, what's A star B? It's this, right?
Yeah.
Okay, and how does phi, what does the map phi do to it? Phi maps any element to the element +1.
Oh, +1. Got it. Thank you.
No problem. Okay, let's call it for today.